Okay, today, hi everybody, today we will see chapter 27, magnetic fields and magnetic sources. As you will remember, the point charge produced electric field which is homogeneously distributed in three-dimensional spherical shape like that, and once electric field line produced, each lines independently went to infinity, reducing its intensity. We learned that, and the intensity is reduced because A equals K times Q over R square, remember? And as the distance increases, the electric field intensity is reduced, okay, inversely with the distance squared. But similarly, if there is a current loop or maybe there is a dipole, okay, the magnetic fields are also created. The magnetic fields are also created. But in order the magnetic field created, you need some kind of current or the dipole. So the smallest unit of the magnetic field, okay, is the dipole. So suppose you have a magnet, north and south. If you just break this into two pieces, consider this case. So originally this was north, but now this becomes north and south. If you just divide this into two pieces, now the small piece becomes now north and south. And if you just keep going to the smallest unit, this is what you can get. So the smallest unit of the magnetic field producing system happens to be dipole, but here is the monopole. So, okay, so that's why the magnetic field lines just are round. Once they are created, they have to come back to their original position which are created. Just like here, suppose that this is the Earth. In the Earth center, there is a magma which rotates this way in counterclockwise direction, so that this part is north, this part is south. So from north, the magnetic field lines go out, just like this magnet case, okay? And south, the magnetic field lines come. But whichever has started from north has to come back to south. So you can never have any independent magnetic field lines. Each magnetic field lines will be able to go back to their original position that they are created. So that's why if you get a total flux on a magnetic field region, okay, the total magnetic flux, which is just integral B dot dA, will be equal to 0 because there is no charge. But for the electric field, so for the electric field, if there is an electric field distribution like that and there is a loop of this kind, we would see that E dot dA is not 0 but equal to Q enclosed over epsilon 0. Why is it so? This is Gauss's law, by the way, because you can have magnetic electric monopole, but there is no magnetic monopole. So this is the basic distinction between the two things. But now this is the total flux that you are considering, okay? But you can see that if there is a wire area and there is a magnetic field distribution, the flux may not necessarily be 0 totally, okay? Also, another version of this integral equation, another version is divergence of B is 0 there, but divergence of electric field is just rho over epsilon 0, rho being Q over volume. Okay, so basically this is another version of Gauss's law. Okay, but this divergence of B is 0, but divergence of E is not 0, is given by this. So these are the two basic equations in Maxwell's equations. Okay, which really relates electric and magnetic field lines together. So now, if there is, we know that if there is some kind of charge distribution like that, either on a wire or just itself, automatically electric field is created. But if these charges move with some kind of velocity, magnetic fields are also created. So then if the charges are moving, it means that there is a current passing through there. And then the magnetic field lines will be just round like this, okay? So they will be more stronger, okay? Stronger when it is closer to the wire, but getting less and less strong when you get away from the wire. But now electric field lines also are produced, okay? if these, regardless of the charges moving or not, electric field lines are produced, guess what? The electric field lines and the magnetic field lines will be totally perpendicular to each other, okay? Like that. So in each direction, the magnetic field lines and the electric field lines will be perpendicular to each other. So when we are considering the current passing through the wire, which produces the magnetic field, doesn't mean that electric fields do not exist. They both exist at the same time. But we just concentrate on now how to obtain the magnetic field distribution and how to obtain the forces on the wire and so on. But now, instead of finding the force on the wire, let's try to find the force on a small charge which is moving with some kind of velocity in the effect of magnetic field, probably aligned in different direction, not necessarily straight. As you see, there is now an angle between the two, okay? So now what happens is that there is a force on this charge as far as it moves, okay? The magnetic force then is given as QV cross B. So the magnitude of this is just QVB sine of alpha, alpha being the angle between the charge velocity and also the magnetic field, not necessarily constant, of course. So now what happens is that by using, suppose that the charge is moving, coming to this region of magnetic field in a straight fashion, but as soon as it enters in this magnetic field distribution, its path is not going to be straight, and because V cross B is this way, the force will be probably this way, okay, the magnetic force, and the path of the charge is now going to be a little bit curved like that. So, because of the force. Now, what happens is that if we consider a simple case, suppose that there is a magnetic field in Z direction, and we give an initial kick to this charge in this direction, okay, just totally perpendicular to the magnetic field direction. In this case, do you know what will happen? This will just rotate around it if it is plus Q, okay? So it will rotate in clockwise fashion in the direction of the magnetic field. So as you see, now the electric field, if there is an electric field, it produces for this charge, okay, for this charge, it produces a force in the direction of the electric field. So the charge just moved in the direction of the electric field in a straight line, okay? As far as the electric field line is straight, the path of this charge is also straight. So the force, the electric force was given as QE, as you will remember. So the direction of the electric field and also the direction of the force were exactly aligned. But now it's opposite, as you see. The force for this one is just, for this one, for instance, suppose velocity is there, V cross B is inside, so that there will be central force, which is central force, which is balanced by the magnetic force, which is outside the page. So the magnetic force will be balanced by the centripetal force, which is mv square over r. Because they are all perpendicular to each other, we can say that for this case, mv square over r is equal to qvb. From this cancels, and then you can get, really, you can get just r, which is equal to mv over qb, where r is the radius of this circle, okay? So as you see, the radius, which is called Larmor radius, okay, now depends on both two things, velocity and the magnetic field, because the mass and the charge, for suppose this is an electron, the charge is known and the mass is known, you can never change these quantities, but you can change the velocity and also you can change the magnetic field. So what happens is that if you change the intensity of the magnetic field and increase it, the radius will be smaller and smaller. For the intense magnetic fields, so the particles will move like that. Why? Suppose that initial kick for this magnetic field is not sideways, but a little bit up like that. In this case, it will not only rotate but also move in a circular fashion, and it will be like spiral motion. Okay, spiral motion. So because of this spiral motion, the charges will move along the magnetic field lines by rotating. Okay, like that. So remember that electric field lines, the charge just moves like that, but here magnetic field lines, not only they move along the magnetic field lines, but also they rotate. And the rotation radius depends on velocity and the magnetic field. So now, if there are both magnetic field and also the electric field in some region, and you put the charge, then here with some kind of velocity, then you know the equation of motion just states that the total acceleration times the mass, which is the sum of all the forces. Remember that the forces, it has to be vector here, was remember in Phys 101 it was just a gravitational force, but now we are adding two things, Q times E plus Q V cross B. If there are electric and magnetic fields, these are the charges. So the summation of these two charges are called Lorentz force, okay? Lorentz force. So depending on the direction and also the structure of the magnetic field and electric field, you can really solve the equation of motion, get acceleration from that, get velocity from this, get position. So it means that you know exactly what's happening with the charge and in what path it moves. You can really control the point that the charge will hit inside a vacuum region, because these experiments can only be done in vacuum, because for small charges you can only make them move when there is a vacuum region. Okay, so basically this is how the magnetic field really is affecting the motion. Okay, now let's go to some experimental facilities that the magnetic field is used intensely. Okay, you know there are two types of fusion devices. Okay, in fusion devices we confine the plasma inside a tokamak. Okay, tokamak is like a donut shape. Okay, and its cross section is like circle on both sides. If you just cut here, the plasma is just confined here. Okay, and plasma has the charges Q. Okay, the positive charges and negative charges, electrons and ions, they just rotate in this case, okay, without touching the walls, because it's so hot that the fusion process is occurring in this region, so that big amount of heat is produced, and because of this heat, the temperature increases to high degrees, and by passing some kind of water pipes from this, you can produce electricity. This is for the next generation of energy production by using tokamak and plasma. And to confine the plasma, they usually have coils like this, strong coils passing maybe thousands of amperes of current passing through these coils, so that you can confine the plasma by not touching the walls because it's so hot. So this is tokamak fusion, and in there the plasma particles motion are just understood by using the equation of motion. And also there is some kind of device, by the way, this tokamak should be under vacuum, so you have to suck the air outside and then put different gases, probably deuterium and tritium or something, so that you can get fusion process. But there is also another machine which is called mirror machine. Mirror machine has two windings on at the edges, so big amount of currents are passed through here, so that there is a magnetic field lines produced, okay, going away from this, okay, so according to the right hand rule, the magnetic field lines will be like this. I will show you, and then they will be really confined like that, and then obviously they will extend, enlarge, but in the middle, okay, in these edges, the magnetic field lines intensity will be high because they will be squeezed in a smaller region. So now the magnetic field intensity, if you go in this z direction, the magnetic field is magnetic field intensity is high here, but now it gets smaller and smaller, and then it becomes high again. So this is the magnetic field distribution in the mirror machine. So what happens is that if there is a charge starting from this part, they will do spiral motion, but now the radius of the spiral motion will get bigger, and then they will get smaller again. And probably they will get reflected into the system, so that by using these two coils on the edges, you can really confine the whole plasma or the charged particles inside this small region. Maybe you can create some kind of energy like that. It's called the mirror machine. But sometimes, because of there is a lost cone here, if the particle just hits in this lost cone, they just go to the right, and if you open a little hole here, okay, in some region again in vacuum, so you can create some kind of beam. So you can do both beam physics and fusion by magnetic mirror. But you know, they have found that there are lots of escapes. Because of these escapes, they just combine the two ends so that there is no escape in the toroidal thing. So the Russian people were the first ones invented the tokamak to create fusion, okay, energy. But see, the Earth also has some magnetic field configuration, because there is a current passing in the magma. Okay, now it's counterclockwise direction nowadays. Okay, so that this is north and this is south. The magnetic field lines go outside from north and go back. Okay, okay, like that to the southern part. So as you see, in the north and south part, the magnetic field lines intensity are so high because they are squeezed in a smaller region. So that in this region, because the magnetic field lines are so strong, the electrons will be really moving extremely fast. Okay, because the magnetic field is very strong. When the magnetic field is very strong, then the very fast moving electrons in this region will hit the ions in the atmosphere or ionosphere and produce different kind of colors. Because when an electron, suppose this is an atom, and electron hits the atom or just gives energy, then the electrons originally attached to the atoms go outside the energy levels, and then they have to come back, of course, because of the conservation of energy. They emit light in all different colors. So because of this light, you can have auroras there, okay? So aurora is nothing but plasma. As you see, also the sun is the plasma, sun, okay? Sun is totally made of plasma, very hot charged particles, electrons and protons. Because it's so hot that probably no atoms can survive. It creates a big amount of energy, but also very bad radiation, very strong radiation that go all the solar system. But because now we have this magnetic field distribution, this very strong radiation just go around the Earth, okay? So this radiation is not really affecting our world, okay? So it means that this magnetic field configuration really is protecting us from the radiation, not only coming from the sun, but also from other astrophysical stars, or some big, you know, massive clusters of giant different kind of planets and things like that. Okay, so this is an astrophysical part. As you see, the plasma is everywhere. Now, in our daily life, we observe that. Also, ionosphere includes a low ionized plasma. Now, can we do some experiment in the lab by using a very intelligent machine? Yes, we can. Okay, but we can only do this by using a vacuum. Suppose we have a vacuum region like that. So we suck the air outside by pump, okay, and put inside some kind of gas that we want, okay. Usually inert gases are used because you need a conducting medium. And what happens is that in this Thomson experiment, let's do an experiment, okay. In this Thomson experiment, we found what is E over m is, okay. We found what is E over m. This is very nice because these are physical constants. And in order to get physical constants accurately, you do develop some kind of experiment. So it's in this highly intelligent experiment, we use lots of physics, okay? So first, Edison type of tungsten lamp, okay, a tungsten wire is heated by applying a voltage here. Because of this, there is an emission, ionic emission of electrons. So electrons are emitted from this wire, okay? And of course, there's a little bit light that you can see there. So, but now if you apply some kind of potential difference between the two plates right across this thing and open some kind of holes in the system, okay, and apply plus voltage here and then minus there, okay. So plus here and minus there, okay. There's an electric field this way, electric field to the left, electric field. Because of electric field, this way the electrons will okay, experience a force in this direction, so that they will pass from these holes, but the ones which are just entering in this second hole, just go outside with some kind of big velocities. It's like a beam, you know, okay? So you create a beam like this, passing from this region with some kind of velocity. Now, can we have a little estimation of this kind of velocity? What kind of velocity we're talking about, okay? So, as you see, by using the conservation of energy here, we have only the potential energy, which is just E times V, okay? Because U equals EV, okay? The potential energy is equal to applied potential difference, which is this. And here, there is no potential energy because of this system, but there is a kinetic energy 1/2 mv squared. Now, if you just calculate the velocity from here, you can find that the velocity is given by 2e, the applied potential difference divided by m. Okay, so as you see now, if you can somehow determine this velocity, which this potential difference here, you can really get the velocity. Now, how can we measure this velocity? There is a way of measuring this velocity. This is not easy, okay? But now what happens is that we put two plates up and down. Suppose this is upper plate and this is lower plate here, okay? So we put these plates and then apply some kind of other voltage, okay? Suppose that this is plus and minus, okay, plus and minus, so that this plus and minus, there is an electric field again. Here we go. In this region, there is an electric field downward. Now we can also apply a magnetic field totally in this perpendicular direction by putting two coils, for instance. I can put one iron yoke here and then another one there, and then put some kind of wires like windings, some kind of number of windings, so you can create electromagnet. And if it is the north and this is south, depending on the direction of the current, for instance here, if the current is moving this direction, this is north, the magnetic field lines will go out. Now the current direction should be, okay, in totally opposite direction, okay? In this case, the current will be there, but the current will be downward here. In this case, north and south, the magnetic field is created like that. So as you see, in this region, there is an electric field this way, okay? And also there is a magnetic field that way. So now the particle is, the charge is moving with some kind of velocity. It's the electric field and this is magnetic field. So under the effect of electric field and magnetic field, then the charge particle will move. Maybe in some kind of path which is like round or something, maybe even rotating because of the magnetic field. But now we're not really considering if these electrons rotate or not. Actually, they do because there is a magnetic field. Anyway, so now we can really balance the electric force with the magnetic force and make that F equals, okay, F equals QE, which is QVB, okay, QVB. We can do that, okay, by adjusting electric field by using this voltage difference V0, and also by changing the amount of current here, okay, in totally applied in the opposite directions, of course, we can really adjust the magnetic field direction and measure the magnetic field intensity, of course. And of course, the magnetic field lines outside this region will have a little bit curvature, but we are not really interested in this region because everything is happening here. Anyway, so we are assuming the magnetic field is constant in straight fashion here. So in this case, when we can adjust V0 such that QE is equal to QVB, then there is an exact balance. And then when this cancels, you can see that V can be written as E over B. So it means that E is measured, B is measured, then V is measured. So this is equal to E over B. So by using this expression, you can find E over M, which is equal to just E squared over 2, okay, the potential difference that you apply to accelerate the electron, okay, divided by B squared. So now E over M ratio is given by this expression, and now by just adjusting, you can really get this bright light on the screen here, so that you have exact adjustment electric field and magnetic field. Then you can get E over M. Actually, without adjustment, these electrons will hit here on the surface or there, anywhere, right? Like in maybe like that. So they will move like that. But by careful adjustment, you can really do this. Okay. So Also, if you can open a little hole here and then put another vacuum region, you can use electron beam. For instance, electron beams are used in scanning electron microscope, okay, which hit the surface and then get the surface feature, okay. So basically, there is a big amount of application once electric field and magnetic field are used in technology, okay. Okay, so this is the introduction of the magnetic field. How they are produced and what kind of experiments we can do in the lab and what happens in the universe and things like that. Okay, so now let's concentrate on the wire. Suppose that there is a wire that the charges just sit there. You remember that? In this case, there is an electric field is produced, okay, like that, okay, like this. Electric field is produced and they are really going away, okay, from this thing, from this charge distribution. It doesn't matter if the charges are on the wire or not. The electric field just will extend, okay, outside like that, okay. But now, what if these charges move? It means that the charge is moving with some kind of velocity. It means there is a current. Don't forget, the current is how the charge amount changes in time. If you open a little window and just the number of charges per unit time within this window just is a measure of the current, you can easily change the current by applying a voltage and a resistance or something like that. How can you do this? Very simple, because you can connect this to a battery, again, DC, okay? Suppose that V0 is applied, maybe a little bit resistance. Each wire will also have some resistance, of course. You don't need to apply any resistance, but there will be instantly some current passing through this. But guess what? Not only the electric field is produced, also magnetic field is produced. So, but the magnetic field is now produced in this like that, or it's like a circular. So the magnetic field is circular, but the electric field is straight. But they are both perpendicular to each other. But not only the electric fields are produced, but also the magnetic fields are produced, okay? They will be totally perpendicular to each other. So once there is an electric field, there is also a magnetic field if the current is passing. But now, if the current is not passing, just electric field always there, but not the magnetic field. But as soon as the charges move, there is a magnetic field which is circular, produced, but also there is an electric field. Although we just concentrate on only the magnetic field, it doesn't mean that the electric field does not exist. Of course it does. Wherever there is a magnetic field, there is usually an electric field associated with it, and also totally perpendicular to it. Like electromagnetic wave, you know, like plane polarized electromagnetic wave, the magnetic field lines are like that, and the electric field lines are like this. So electric field lines will also oscillate plus and minus, but they are all perpendicular to each other, okay? Always. So this is plane polarized. If this is the electromagnetic wave, okay? But now, if there is a circular polarization, the magnetic field line, electric field line will rotate, okay, as the magnetic field wave moves in atmosphere. The electromagnetic wave can also move in the empty space, okay, but they have to rotate. The magnetic field and the electric field lines rotate, whatever. So in order to understand this, you have to really understand why this thing is happening. Now, what happens is that, you know, if you now, let's concentrate on the force. Remember that the force for the magnetic field is given by Q V cross B, okay? So the force on the electric field was QE, okay? The force this was electric force. So this is the magnetic force. So now you remember that. But now, suppose we have a segment of wire, say L, and then you can write velocity as L over T, but Q over T here is written as current, then current times L cross B you will have. So the magnetic force on the wire, will be given as, okay, just L cross B, okay, if this is L, the distance, okay. But now the L is a vector in the direction of current, okay. Whatever the direction of the current, okay, the L vector also is going to be in the same direction, and this is the length of the segment. So if you want to get the total force on this wire, you have to get the total length okay, put here capital L if the total length is L and get the total force. But you have to be careful because now the direction of the current should have some kind of angle with the magnetic field. Of course, in order to create this, you need a magnetic field distribution. Otherwise, this current passing through a wire in which there is no magnetic field really will not experience any force. So don't forget, B is external magnetic field. External magnetic field. But this magnetic field that is created from the current is internal magnetic field. So this is just a self-magnetic field. So this magnetic field is self-B field. Don't forget, we are putting the wire in an externally produced magnetic field and see what happens. Of course, this wire will also produce its own self-magnetic field. And guess what? This self-magnetic field will interact with the external magnetic field, and you will get some kind of force experienced by the whole wire. So this is how the physics works. Okay. Now we will do some kind of we will solve an example by this. It looks a little bit complicated in three dimensions, but once you understand the problem, you will see that it's really not difficult to handle. Even this kind of complicated problems can be done easily if you are really careful with the geometry and everything. So suppose that we have now this direction of z there and then x there, okay? So x direction is extending here and z there. And obviously if this is x, this must be y, okay? So y is this. So that x cross y gives you z. It's correct. So all of these x's are really 90 degrees to each other. Now, what happens is that we put some kind of wire, we just put the wire like that in this direction, and then put in a semicircular fashion, okay, and then just extend it to the right. So we pass a current, okay? We pass a current. We can do that by connecting this wire to a power supply. It's easy. But as you see, this part is just 90 degrees. It's perpendicular to this direction. So now we also apply an external magnetic field, which is in this direction. So the magnetic field direction which is applied is going to be in this direction. As you see here, totally aligned with the current, but here perpendicular, so that now it's going outside from this surface. So the same value at each point, by the way, constant magnetic field, but here totally perpendicular. So this is also 90 degrees there. Okay, so now the magnetic field, if you just look at the segment, the magnetic field will also have 90 degrees, so that we don't need to consider the sine alpha, because in each segment we will calculate now the total force. So say this is segment number 1, this is segment number 2, this is segment number 3. Now in this first segment, okay, in the first segment, the magnetic force is 0. Why? Why? Because the direction of the magnetic field and also the direction of the current are aligned in z direction. One is in plus z, the other is in minus z, so that the angle between them is 180 degrees, but sine of 180 degrees is just 0. Because why? Because remember that F equals I L B sine alpha. If there is a vector product, this is what you get. This is the magnitude of the magnetic force. And then this alpha being the angle between the current and the magnetic field. Here in this case it's 180 degrees, so that it's 0. So don't forget we are using this, but for each region 2 and region 3, alpha is 90 degrees for segment, okay, segments 2 and 3. So we don't have any alpha dependence here. So that for segment number 3, for instance, it's very straight one. It's simple. It's just ILB, L being this length. Okay, this length is L, let's say. Okay, so the total force on this segment 3 is going to be in y direction. How do we understand it's in y direction? Because remember that the current is in this direction, the magnetic field in that direction. I cross V just gives a force in upper direction. So I don't have any other color, so that I will put now the force in this direction. but this is y direction, by the way. So the force on the third segment will be totally in y direction. What about this part? This part also the same idea, although it's not straight line, but it's perpendicular to the magnetic field line. At each point, the force again will be aligned in y direction by using I cross B business. So the force is just L I cross B, okay? But L now is not straight. You have to be careful how to obtain this. Now, to solve segment 2, okay? Segment 2, we just concentrate on this by looking from this side, okay? Suppose that your eyes are looking from this side, and this is exactly what we see, okay? So here is our wire. Now here in this part, okay, the current is passing through here. So the current is going down and then doing this and then going to the left. But now this direction is minus x direction. This is x, by the way. Okay, this x, just like here, x. Now this upper direction is y, as you see. Okay, this is the reason that we chose this, because I would like to show you something. Because now, because it's round, it's not straight, it's not easy to find the total force on this wire. Why? Because it's now the length or any dl that we consider from this part is not straight, but it's just curved. So at each part there is a little bit distance, and then this distance is making an angle theta there, and then this is d theta. Just like Phys 101, remember that in rotations you did this angle and then just a little bit angle. So this dl, and if the radius is r, dl is just r times d theta, okay, with some kind of unit vector, okay. dl vector is always like that. So this length of this thing is r d theta. If you measure this d theta as 2 pi, is 2 pi r, which is the circumference of this total length around the circle, but we just have the limit from 0 degrees to 180 degrees. Don't forget. So theta minimum is 0, theta maximum is just pi, which is 180 degrees. Okay, so we would like to see the effect of this what about the magnetic field distribution here? As you see, magnetic field is now passing through upper direction, but here now the magnetic field is going up. Okay, so it's outside the page now, the magnetic field line. The magnetic field lines are now going up like that. So if the magnetic field line is going up and the current is going down, the force is just the other way. So if for this segment, the force will be like that, and it will be called as dF. Now let's do this in a bigger shape here. So that here now we have that. So now this is center of this circle. So we have just dF there due to this dl. Okay, this dl. So this angle d theta is so small that this dl is not curved but just straight. And this is, don't forget, theta, and this is r. So df now has two components, dfx and dfy, basically. Why? Because this is y direction and this is x direction. So we have to consider both components, x and y components of this force. Now, this angle theta there also, the same angle. So how can we get this? Very simple, because this is just df times cosine theta, but this is df times sine theta. But do you know what? On this side, exactly the symmetric, okay? So the force is this way, and this is dfx, and this is dfy. Guess what? These cancel that one. So x components will be canceling out because there is a symmetry, okay? So they cancel each other so that we have no effect. And by integrating, we will be able to see that really the total force in x direction is 0, but there is a net force in y direction. So how can we do this? So in order to find this, I have to write df, but df is given by just I times dl times b. Sine alpha, but alpha is 90 degrees, right? Alpha is pi over 2. That's why this is just 1. Okay, this is just 1. I don't even consider this angle. I told you that perpendicular. So the magnetic field lines are outside the page like that. So perpendicular to dl, as you see. This is dl, and this is magnetic field, as you see, 90 degrees. Good. So now, how can I write this expression? including some angle. Don't forget that df is I times, instead of dl, I'm writing just rd theta. Okay, r times d theta times magnetic field there. Now, dfx, however, is just I, R, B, sine or cosine, which one? Sine theta, d theta. So when you integrate, okay, so these all constant taken outside, you get total f in x direction, in y direction, sorry, y direction. So y direction, again, df times sine theta, right? X directions cancel each other. So this is fy. And now let's see what we get from 0 to pi. So integration of sine theta is minus cosine theta. But if you put the limits from 0 to pi, you get exactly 2, plus 2, because cosine pi is minus 1 and cosine 0 is 1, and there is another minus sign which makes it plus 2. So the total force in y direction is 2IRB. So this is it. What about f of x? Okay, so what is the force in x direction? Again, IRB, but now cosine theta, d theta, from 0 to pi. As you see, the integral of cosine theta is sine theta, but sine theta is 0 at both 0 degrees and also pi, which is 180 degrees. So that this is 0 and f of x is 0. So that the total net force in this segment of the wire is in y direction, and here in this segment it's again in y direction. So the total net force then, F net as a vector, is equal to just I L B plus 2I R B, or if you factor out B and I, so that IB times L plus 2R. As you see, the net force on this wire is upward. So this whole wire will be lifted up if there is a magnetic field in this direction. Okay? If the current is also passing through there. As you see, we have never considered the electric field, just considered the magnetic field, and the existence of the magnetic field created a force when the current was passing through in this three-dimensional segment of wire, where the first segment didn't experience any force, but the second and the third segments experienced a force in totally in y direction. Okay, so this was an interesting example. Now we solve another example if we have enough time. Okay, we have just a little bit time, so that quickly, okay, we now complete another experiment that we can do in the lab. Okay, we can do in the lab. So it's called current balance experiment. Current balance. So we have a very sensitive balance. Balance measures your weight, as you know. Okay. So in this balance there is a screen. Okay. In this screen probably it writes the weight in grams, let's say. So suppose that you put here on the top some kind of okay, matchbox like that. Okay, put neodymium magnets just facing each other. Okay, like this. Okay, so neodymium magnets just facing each other like that, and obviously this will have some kind of weight, and then its weight will be seen probably, let's say 160 grams. Okay, 160 grams that is showing because of this thing. So now just keep it that way. In this case, because we can really adjust the direction of the permanent magnets, one side can be inner surfaces, of course, when maybe north, and the other side south, and then the magnetic field direction will be from north to south in here, like that. So magnetic field direction will be in this way. Okay, so if you call this as x direction, the magnetic field in x direction. But now there is also this direction, which is y. Now we put a cable like this, passing through this region like that, and then going up. So the total length is just L, let's say, and the current now passing through this is adjusted such that there is a force on this system, on this matchbox, including this permanent magnets, in the direction opposite to the gravitational direction. Okay, mg is downward. It's probably x, y, z minus z direction. Okay, so z is this direction. Okay, so mg is in minus z direction. Okay, so we pass a current, but now if the magnetic field is this way, and the current will be either to the right or to the left in this region, these regions do not matter because they don't experience any magnetic field, no force. But here there is a big amount of force, but we would like to do the force such that it's opposing to the gravitational force, so we want it to be in this direction. So the magnetic field force should be in this direction, opposing to the gravitation, so that probably we can reduce the weight of the whole system. 160 grams will be reducing to some kind of other weight when the magnetic force is applied upward. So how come is it possible? So if the current is to the right, as you see, if the current is to the right, I cross B is downward, but if the current is to the left, I cross B is upward. So the current should be applied in this direction. So we apply a current, and then there is a magnetic force, and the magnetic force is just given as just ILB, okay, L being the distance between the permanent magnets, usually a few centimeters, okay, and the current in the order of 10 amperes or 5 amperes, whatever. So now it is totally balanced by mg, okay. Now see what happens. Now suppose that in this experiment we apply 10 amperes, and the typical magnetic field from the permanent magnet is in the order of 0.2 Tesla or something. This is huge, by the way. Very strong magnetic fields can be created by these niobium magnets, and really it's a high technology. We have to have a factory which produces very strong magnets so that we can make some kind of motors that we will see that all the motors or energy production depends on how strong you can create the magnetic field and how to manufacture them. Anyway, so magnetic field is given by this value, and the current is 10 amperes, and let's say that L is 5 centimeters, okay? So 5 centimeters is just 0.05 meters, so that if you put the magnetic force, it's just ILB, and it will be 10 times 0.2 times 0.05, which gives you 0.1 Newton, okay? But this 0.1 will be equal to mg, or this kind of force will be created in upward direction, okay? It's the force opposing to, okay? This is the force that is created by the magnetic force. They say the magnetic mass or something like that. So this is magnetic mass reduction, let's say. So from here, G is 9.8. If you divide the other side, you see that the magnetic mass efficiency will be given by just 10 grams, okay? It's in kilograms, but if converted to grams, this is what you get. So as soon as you apply 10 amperes, do you know what happens? This C now, omega new weight is just 150 grams. So it reduced the mass of this whole matchbox, including the permanent magnets, okay, by applying only 10 amperes, okay? So now, suppose that you keep the magnitude of this weight of this whole system as 10 grams. In this case, by applying 10 amperes, you can hold it in the air. You can just hang it by using just a wire and passing 10 amperes. So this is beautiful experiment that the current really produces a big force when there is a external magnetic field, in this case created by the permanent magnets. Okay, this is the end of the lecture today, and we now get ready for